This is the 2018 AQA AS Physics Paper 2. A few general comments that the examiner's report made about this paper. Generally, a lot of students struggled with the analysis and interpretation questions, so it's important that you really do practice these type of questions before the exam, because they were surprised at the number of non-attempted questions, which also included calculations. So, calculations are something that you should have been practicing for all the way through the A level, and you're given a lot of the information. So they suggest that students develop a better appreciation of the question layout of the paper and understand the scaffolding that's provided to help them answer the question. They've said that students should summarize the data that's provided and identify the quantity to be determined. Then inspect the formula sheet, and that quite often allows at least some progress to be made. Whilst doing the calculations, they suggest that you lay them out in a vertical columns to make sure that it's easy to follow, and show the equations that you're going to use, because then at least you're going to get partial marks for going part of the way through the question. They've also said that quote answers to an appropriate number of significant figures, as a lot of students aren't doing that. So the number of significant figures you should be using is the number of significant figures of the data with the least number of significant figures. But I'll show you some of these examples as we go through the paper. Question 1 shows us some apparatus used by a student in an experiment to measure the acceleration due to gravity. So we've got some light gates and an air track, and it says that a block was used to raise one end of the track. An air track glider is released from rest near the raised end of the track and passes through the first light gate and then through the second. A piece of card of length D is fitted to the air track glider and interrupts the light beam as the air track glider passes through the light. So make a note that D is the length of the piece of card. A data logger records the time taken by the piece of card to pass through each light gate, and also the time for the piece of card to travel from one light gate to another. Okay. So what we've got here, table 1 gives us the measurements made with the light gates. So we've got time to pass through light gate 1, time to pass through the second light gate, and the time to travel between them both. It says the length D is the piece of card, which is 10 centimeters. Assume there's a negligible change in velocity while the air track glider passes through the light gate. Determine the acceleration. Okay. So first thing we need to do is work out the initial and final velocities, because the information that we're given is we want to find acceleration. We're given a time that it's taken to travel, but what we don't know at the moment is the initial and final velocities. So to work out this, we can work out U, and remember, velocity is distance over time. So in this case, the initial velocity, D, is 10 centimeters, so that's going to be 0.1. And the time taken to pass through the first light gate is 0.5. So that will equal 0.20. So this, by calculating the time that it takes to pass through the first light gate, that's what its initial velocity is. So it can work out the final velocity in the same way by calculating the velocity that it has when it passes through the second light gate. So V equals, again, the distance is going to be the same, the distance of the card, which is 0.1, but this time it takes 0.4 seconds, so that is going to be 0.25 meters per second. So now we've got those two values, we can just use an equation of motion and rearrange it. So A is the subject, so A will equal V minus U over T, and that will be the 0.25, which we've just calculated, minus the 0.2, which was our initial velocity, over the time it took to get between the first and the second light gate, and that is 1.19 seconds. So the acceleration will come out to be 4.2 times by 10 to the minus 2 meters per second squared. So 1.2 says two further sets of readings, A and B, are taken, each with the light gates at different positions along the air track. Assume the acceleration is the same in each set. So we're given set A, and again we're given the time for it to be passed through the first light gate, the second light gate, and then the time to travel between the two of them, and we're given the same information for B. Explain how the data in table 2 show that the distance between the light gates in set B is greater than set A. Assume that there's negligible change in velocity while the air track glider passes through the light gate. So we can see already that the time taken to travel between the light gate in B is longer. So it's 2.11 seconds there, but it's only 1.77 seconds in A. Now, a lot of students just put that, because this distance in B is greater than the distance in A, therefore it must be longer. Now, you've got to develop the argument a lot more, because yes, it's taken longer to travel, but it would also take longer to travel if it wasn't traveling as fast. So if the cart was traveling at a slower velocity in B, it would also have the effect of increasing that time. So we've got to fully develop the argument. So what we can look at is the times passing through both gates. So we can see that the time that it takes to pass through gate 1 is less in B than it is in A. And also, if we look at the times for it to pass through the second gate, again, it's less in B than it is in A. So what we can imply from that is, because the time travelled through the gates in both cases is lower, then B must be travelling at a greater speed, a greater velocity in B than A. So now we've determined that it's travelling at a greater velocity and it's taking a longer time. That's how we can then say that B is the gates in B are at further distance. So it isn't just a case that it's taken longer to travel, it's taking longer to travel and it is travelling at a greater velocity. Now you could have done this, you could have carried out the calculations, and you could have carried out the calculations and found what the velocities were in A and B in both light gates, but just by looking at the times it's taken to pass through, we can see that it's a greater velocity. So what we can say for the answer is that in B, the time through both light gates is less than times in A. Therefore, U and V must be larger in B, and also the time to travel between the gates is longer. Therefore, distance must be greater. So you've got to think about the aspects that would cause that greater time to pass between the light gates. So yes, it can be a greater distance, but it could also be because they're travelling at a lower velocity, and because you've done these calculations, or you've explained how the shorter times means that U and V must be greater, then you're getting rid of that part of the argument and concentrate on the distance between the two. Right, so part 3 says additional values for the acceleration of the air track glider were obtained by further raising the end of the air track by using stack consisting of identical blocks. Adding each block to the stack raised the end of the air track by the same distance. Figure 2 is a graph of these results showing how A varies with N, the number of blocks in the stack. Draw a suitable best fit straight line on B and determine G, the gradient of your line. Now, when you draw the gradient, make sure that it's a continual ruled line. And also make sure that your pencil is really sharp, so the line itself is very thin, because the thicker the line, then the more uncertainty there is going to be when you're looking at positions of points. So make sure that you've got a nice, sharp, straight, continuous line when you draw your graph. And we know that the gradient is going to be the y value over the x value. Now again, when you use your triangle, make sure that you draw your triangle as large as possible to get the gradient. You should be using at least half the grid in both the x and the y direction. So I did this on the actual paper itself and got a value of G to be 0.045. Okay. So the next part says it can be shown that for the apparatus used by the student, the G, small g, is equal to 2 capital G over H, where H is the thickness of each block used in the experiment. The student obtains a value of small g, gravity, to be 9.8 meters per second squared. Calculate H. So we know that 9.8 equals 2g over h. So that's 2 times by the value that we've just calculated from the gradient, which is 0.045 over h. So we're given that in this equation here. So we can work out h to be 0.09 over 9.8, which equals 9.2 times by 10 to the minus 3 to 2 significant figures. Because remember, we're using the number of significant figures in the data that have been given in the question that has the least number of significant figures given, which in this case is 2. Right, a lot of students had problems with this final part of this question. It says explain how you could find out without drawing another graph whether the data presented in the graph in figure 2 supports the suggestion that A is directly proportional to N. Now a lot of students disregarded this without drawing another graph and described an experiment where another graph would need to be drawn. Also, they didn't really appreciate the significance of that term directly proportional. So the common error was that they were thinking that a linear relationship was the same as directly proportional, and that's not the case. Now we can see in the graph that if we just have a quick look at the graph again, we can see that the graph here doesn't go to 0, 0. We've got n as 1 and a as 0.05. So if we drew a straight line on this graph, we don't get to see an axis intercept. Okay, and that's why a lot of students were talking about redrawing a graph so we could actually see an intercept, but we don't need to draw a graph, another graph, to see what the intercept is. So what we can do is we know, because it's a straight line graph, that y equals mx plus c, where c is our intercept. So in this case, it's a, the acceleration, equals gn plus c. So again, on our graph, the y-axis was acceleration, the gradient was g, and on the x-axis was n. So what we can do is we can take various points on our graph and feed them into this equation to calculate c. So c would equal a minus gn. So we know that the value of g. So for any value of n, we can use our graph to see what a is and then calculate a value for c without the need for drawing another graph. So we can say that can calculate c by reading off a and n from the graph. If y-intercept is 0, this shows a is directly proportional to n as graph is straight line through the origin. And that's a point that a lot of students missed, that it isn't just that it's a straight line, it's actually got to pass through the origin too for it to be directly proportional. Question 2 shows us two identical ring magnets A and B that are arranged on a cylindrical wooden rod. The magnetic poles are on their largest faces. When they're placed with like poles in opposition, the magnets repel one another, as shown in figure 3. So we've shown the different dimensions of them and the setup of the experiment. So part 2.1 says a student uses a digital vernier calipers to find the external diameter D of the magnet B, as shown in figure 4. State the precautions a student should make to reduce the effect of systematic and random errors while making the measurement. So we want to rule out systematic and random errors. Okay, so for the systematic, the systematic error is the error that you would be constantly getting during an experiment. So for example, if the calipers were not zeroed, if they were at 0.1 for example, even though the calipers are closed, you'd always get that error on the diameter. So to reduce the effect of the systematic error, we would zero calipers. Now, to reduce the effect of random errors, this might be an error in measuring the diameter. So you might not get the full diameter. It might not be you're placing the calipers right across the disc. So what we need to do is take the measurement of the diameter in several places, and again this makes sure that the area of the disc is circular and it isn't narrower in one part than it is in the other. So this is the type of question you've got to give enough detail in. So it's not just enough to give an answer like repeat measurements and average. You've got to say what you're repeating the measurements of. So we would say take measurement several times for different diameters and calculate mean. Okay, so you're actually telling the examiner what you're taking several measurements of. So the next part says figure 5 shows the reading on the calipers as an internal diameter is measured. Draw the sectional view of the magnet B on figure 5 to indicate how D is measured. So because we're choosing the internal one, it's best to use the measurement on top. So what we would do is place the inside of the magnet here. So this part here is the magnet, as is this, and this is the internal diameter. So the inside jaws in contact with the internal diameter. And a lot of students didn't really show a knowledge of using calipers, so make sure that all the equipment that you're expected to be familiar with during your A level, you've actually familiarized with this and know how to use and take measurements with. Okay, figure 6 shows the reading on the calipers when the thickness T of the magnet is measured. Use the readings that correspond to the dimensions of the magnet B as shown in figures 4, 5 and 6 and calculate the volume of magnet B. So because it's a disk, we know that the area of a disk is its area times by its thickness. Now of course in this case we've got an internal disk that's missing, so we've got to subtract that from our volume of the disk. And we've been given all the values now of the diameter of the disk, the internal diameter and the thickness. So the way to calculate this, we know that the area of the disk will be pi r squared. So it's going to be, we can take pi outside a bracket, and it's going to be 59.9. Now remember, this is the external diameter, so we're going to need to divide that by 2 to get the radius. So this takes into account the area of the external diameter, and we're going to subtract the area of the internal diameter, that the internal disk is missing, and because we've already got pi out of the bracket, we can just do 19.32, and again divide this by 2 because it's a diameter squared, and we multiply that by the thickness of the disk, which is 12.09, and that comes out to be pi 29.5 squared minus 9.66 squared is like 12.09, and that comes out to be 3.05 times by 10 to the minus 5 meters cubed, because we want the answer in cubic meters as in the question at the bottom. So again, while doing this calculation, make sure that you have set out the calculation in an order so the examiner can follow it, and therefore if you do make a mistake part the way through, you do get partial credit. Okay, so it says the student measures the mass MB of magnet B and then positions the magnet so that it is in equilibrium above magnet A as shown. And the student measures the distance h. The student adds modelling clay to magnet B to reduce h by 50%. She measures the mass of clay, which is MC. she concludes that the force exerted on magnet B by magnet A is given by F equals K over H cubed, where K is a constant. Describe an experiment to test the student's conclusion that F equals K over H cubed. So the way that we can test this is we can, for different values of F and H cubed, we can plot a graph. Now if this is true, we'd end up with a graph of y equals mx plus c. So what we would get is a straight line graph if we plotted y against x. We get a straight line graph, there's no c, so that would be through the origin, and m would, the gradient of this graph would be k. So we've got to get different values of the force. Now what we can do is add different amounts of clay to our magnet. So if we add different masses of clay, that's changing its weight, so its downward force. And once it's in equilibrium, that downward force, that downward weight, would equal the force that's exerted on the upper magnet by the lower one. So we can get the values of F by knowing the weight of our magnet plus the clay, and we can measure H. So we can then plot a graph to see whether it's a straight line through the origin, and by calculating the gradient of that, we can get a value of K. So we need to set that out to describe what we're doing. So we can say we can take more measurements for more masses by adding different amounts of clay. Convert total mass, i.e. the magnet plus clay, into weight. So the weight will equal the force of mass of magnet A on magnet B. Then we can plot a graph of F against 1 over H cubed. So after measuring H for each value of F, so just making sure that the examiner knows that we've calculated H, or we've measured H for each different mass of clay that we've put on. We can then draw a straight line of best fit and measure gradient which equals K. So a lot of students doing this exam lacked the detail how to vary the mass. So that's why we're putting a lot of detail into the question. We're saying that we're adding different amounts of mass and we're converting this mass into weight. And the weight equals the force of the magnet A forces on B. So when we're leaving the examiner in no doubt about the steps that were taken and why we're doing them. And some students also didn't know how to process the data once they'd got them to produce a straight line graph. And so what we've done is we've gone through and explained every single step, including what graph we would plot and what we are going to measure and calculate to get the actual value of K. So question 3 tells us a radioactive source emits alpha particles, each with 8.1 times by 10 to the minus 13 joules of kinetic energy. Show that the velocity of an alpha particle with kinetic energy 8.1 times by 10 to the minus 13 joules is approximately 10 to the 7 meters per second. And we're given the specific charge of an alpha particle. So there's a couple of ways of doing this. So one way is we know that energy, kinetic energy, is half mv squared. So we're being asked to show that what the velocity is. So we know what the energy, kinetic energy, is. So we need to find mass. So an alpha particle mass equals 2 times by 1.673, which is the mass of a proton, plus 2 times by 1.675, which is the mass of the neutron, times by 10 to the minus 27, and that comes out to be 6.696 times by 10 to the minus 27. So we know that E equals half mv squared. So V equals root 2e over m. So if we plug these values into the equation, we get V equals 2 times by 8.1 times by 10 to the minus 13, being given, divided by the mass that we just calculated, which was 6.696 times by 10 to the minus 27, and that gives us 1.56 times by 10 to the 7, which is approximately equal to 2.10, 2 times by 10 to the 7 to one significant figure, which is what we've been asked to show in the question. We could, rather than calculate the mass by adding the mass of protons and neutrons, we could have also used Q over N equals the 4.81 times by 10 to the 7, which is the specific charge of the alpha particle that we've been given the question to find M. So either way of finding M would have done, and then done the same thing about substituting that in the E equals half mv squared equation. So question part 2 says the alpha particles travel through and straight lines with a range of 3.5 centimeters. Calculate the average force exerted on an alpha particle as it stopped. So we know that it's taking 3.5 centimeters to stop, and we know the equation work done equals force times by distance. So we know that the work done, because that's the amount of energy, the kinetic energy that the particles have, and for them to be stopped, that kinetic energy has got to be reduced to 0. So that amount of work done has got to be applied. We know the distance, which is 3.5 centimeters, so we can calculate force, which is going to be the work done divided by the distance, which comes out to be 8.1 times by 10 to the minus 13, which were given in the above question, divided by distance. Remember to convert to meters, so that's 3.5 times by 10 to the minus 2. So force comes out to be 2.3 times by 10 to the minus 11 newtons. Next part, it says an alpha particle transfers all of its kinetic energy to air molecules and produces 5.1 times by 10 to the 4 ions per centimeter over the range of 3.5 centimeters. Then it says calculate the average ionization energy in electron volts of a molecule of air. So the first thing we need to do is calculate how many ions are actually formed. We're told that it produces 5.1 times by 10 to the 4 ions per centimeters, but we're traveling for 3.5 centimeters. So the number of ions formed equals the 5.1 times by 10 to the 4 that's produced every centimeter times by the 3.5 centimeters, and that gives us 1.785 times by 10 to the 5 ions. So we've been asked to calculate the average ionization energy for a molecule of air. So we know that the amount of energy that the particle that we started with was 8.1 times by 10 to the minus 3, and that's given to 1.785 times by 10 to the 5 air molecules. So the amount of energy per air molecule is going to be, so the E per ion is going to equal 8.1 times by 10 to the minus 13, which is the kinetic energy of the alpha particle, divided by the 1.785 times by 10 to the 5 air molecules, and that comes out to be 4.5378 times by 10 to the minus 10. Now that's in joules. We need to convert it to electron volts as stated in the question. So we're going to divide that by our 1.60 times by 10 to the minus 19. So this is in joules. And that comes out to be 28.3 electron volts, or 28 electron volts to our two significant figures, which is the significant figures that were given in the question. So 3.4 says there's a spark counter consisting of a wire gauze separated by metal wire by a small air gap. The power supply of an output of 4,500 volts is connected in series with 5 mega ohm resistor and the spark counter shown in figure 8. When the radioactive source is moved close to the wire gauze, sparking is seen in the air gap. So we're given the diagram there. Sparks are produced when the alpha particle produces ionization in the air gap. One ionization event produces a current of 0.85 milliamps for a time of 1.2 nanoseconds. Calculate the number of charge carriers that pass a point in the connecting cable during this ionization event. Okay, so we know that the total amount of charge transferred, Q, is going to be the current is the amount of charge per second. So the total amount transferred is going to be our current times by time. So that's going to be 0.85 times by 10 to the minus 3 times by our time, which is 1.2, and don't forget it's nanoseconds, so that's going to be times by 10 to the minus 9, and that comes out to be 1.02 times by 10 to the minus 12. So the key here is remember your prefixes. We're talking milliamps and nanoseconds, so don't forget the appropriate values. So N is, so we know the amount of the total amount of charge carried. Now we know the charge on each ion is going to be 1.6 times by 10 to the minus 19. So all we need to do is divide the total number of the total amount of charge transferred by the amount of charge that each ion carries. So that's going to be N equals 1.02 times by 10 to the minus 12 divided by the 1.6 times by 10 to the minus 19, which is the charge that each carrier can carry. So N comes out to be 6.4 times by 10 to the 6. So here what we've done is, from knowing the current and knowing the time that the current is on for, we can work out the total charge, and we know that how much charge can be carried by each charge carrier, so therefore we can work out how many charge carriers there are. Now this is a question a lot of students struggled with, and only 10.7% of students actually got any marks at all. And it seemed to be that because of the number of factors involved in the question, a lot of students found this too challenging. But if we break it down into what's going on, so we've been told that a radioactive source was positioned 10 centimeters above the wire gauze before being slowly moved towards the wire gauze, leading to an ionization event. Discuss how the potential difference across the air gap varied as the radioactive source moved across over this distance. Assume that the power supply has negligible internal resistance. So if we just have a look at the diagram again, we can see that what we've got at the moment, we've got this 4,500 volts supply here, got 5 mega ohm resistor, and we've got this radioactive source. Now when this radioactive source is 10 centimeters away, we know that ionization is only going to occur when it's within 3.5 centimeters from the gap. So when it's 10 centimeters away, there's not going to be any ionization between the gap here, and therefore there's going to be no change in the potential difference across this gap, because there's going to be no ionization during that gap. Okay, so when the ionization occurs for less than 3.5 centimeters, so once the source gets within 3.5 centimeters of this gap, then we're going to get charge carriers liberated in this gap here. So once there's actually charge carriers liberated, then the resistance in the gap is going to be lowered, and that's going to allow current to flow across the gap. And because essentially we're then going to have a resistor in this gap, it's going to be in series with this 5 mega ohm resistor that's in the circuit. So if we start writing about what's going on step by step to see where we can get the marks from, we can say that when 10 centimeters away, there's no ionization, as range of the particle is 3.5 centimeters. Therefore, there's going to be no change in PD across gap. Okay, so when ionization does occur in the gap for distances less than 3.5 centimeters, that's when we get charge carriers liberated in the air gap. Therefore, the resistance lowers because there's more charge carriers there, and that allows current to flow. Okay, so what's then going to happen to the potential difference? We've been told that current equals 0.85 milliamps, and the total R is going to be our 5.0 mega ohm plus the R across gap. Okay, so we can calculate the V across our 5 ohm resistor. So V across 5.0 mega ohm equals V equals IR. We know the current is 0.85 times by 10 to the minus 3, and we know we've got a 5 mega ohm resistor, so that's 5.0 times by 10 to the 6. So V equals 4256 volts across the 5 ohm resistor. And because of Kirchhoff's law, so using Kirchhoff's law, then the V across air gap equals the 4500 minus the 4250 across our 5 ohm mega ohm resistor, so that's going to equal 250 volts. So what we've done, we've described how there's no change in the potential difference across the air gap because there is no charge carriers there. But as soon as we get within 3.5 centimeters, ionization is going to occur, and therefore we've got some charge carriers, which means that current flows, we've got a reduction in resistance, so therefore we can see how we can then calculate what the potential difference across that gap is. Question 4 gives us a ray diagram of an instant ray of light being partially reflected at a boundary between two different glasses, and we're given the refractive index of glass A. We're told the speed of light of B is 3.252% less than the speed of light in A. And we're given a little diagram. It says calculate the refractive index NB of glass B, and we're given the speed of the light in vacuum. So we know that the refractive index is the speed of light in a vacuum divided by the speed of light in that material. So NA equals C over CA. So if we rearrange that to find out the speed of light within glass A, we've got 2.998 times by 10 to the 8, which is the speed of light in a vacuum, divided by the refractive index of A, which is 1.461, and that comes out to be 2.052 times by 10 to the 8. So we're told that the speed of light in B is 3.252% less than the speed of light in A. So we can calculate the speed of light in B, which is the speed of light in A, which is 2.052 times by 10 to the 8, minus the percentage difference of 3.252, which comes out to be 6.673 times by 10 to the 6, and that equals 1.985 times by 10 to the 8. So to work out the refractive index of B now, it's just the speed of light in vacuum, which is our 2.998 times by 10 to the 8, divided by the speed of light in B, which we've just calculated, which is 1.985 times by 10 to the 8, and that gives us a value of 1.510 to 4 significant figures. Part 2 shows us a figure of optical fibre strain gauge, where we're given the instant light, the reflected light, and regions of core with the increased refractive index. we're told that a maximum intensity of the reflected light is produced due to superposition of the light reflected from each of the regions with increased refractive index in the core. The maximum intensity occurs at a particular wavelength, lambda r. Figure 11 shows the relationship between lambda r and the strain in the optical fibre. So we're given this graph here. It says a cable is used to raise and lower a lift. An engineer fixes the optical fibre strain gauge to the cable to monitor changes of the strain in the cable. The lift is initially at rest and then accelerates downwards for a short time before reaching a constant velocity. Discuss how the value of lambda r changes. So one thing we do know is that a decrease in tension, the stress, causes a decrease in the strain, and we can see in that graph that this would result in a decrease in lambda r. Now, as a lift accelerates downwards, there must be a resultant downward force, because we know that F equals ma. So if it's accelerating downwards, then there must be a resultant force downwards. Now the weight of the lift is going to stay the same, so that means the tension in the cable must be less as it's accelerating down. So because as the accelerates downwards, tension is going to be less than the weight, then you get with a decrease in the tension, you're going to get a decrease in lambda r. But at constant velocity, the tension equals the weight because we've got no overall acceleration, so there's no overall force. So now we've got the tension is the same as when the lift was stationary, so lambda r is going to return back to its initial value. So if we put down the type of things that we'll get the marks for, so we can explain that a decrease in tension, so that's the stress of the cable, causes a decrease in strain, and that results in decrease in lambda r. So this part is just using the graphical information that we've been given, and we're applying that to the tension in the string. So we can we've linked any change in the tension of the supporting cable of the lift, while relating that to lambda r. So now we can actually talk about how the tension is going to change during this journey of the lift. So we can say that as the lift accelerates downwards, the tension is less than the weight. So a decrease in tension results in decrease in lambda r. But then it reaches constant velocity, the tension equals the weight. Therefore, lambda r returns to initial value at rest. So some of the things that the students couldn't do during the exam, they were able to make the link between the motion of the lift and the strain. So, if they couldn't describe that, then obviously they couldn't describe what was happening to lambda r. But it's all about, when you think about, if things are accelerating, there must be an overall force in a particular direction. So if it's accelerating downwards, then there must be an overall force acting downwards. So the last part of this question gives us a relationship between lambda r and the strain in two different optical strain gauges, P and Q. And we're told that the engineer wishes to measure small accelerations in another lift. She can choose to fix either of these to the lift's cable. And we're asked to explain which gauge the engineer should select. So we can see here that over the same strain, the difference in the change of lambda r is much greater in P. So for the same change in strain, we get a much larger change in lambda r. And if we're talking about small changes in strain, which would result from the small accelerations, then what we want to do is make those changes in lambda r as large as possible. Okay, because the larger the value, then the less uncertainty we're going to get in the measurement. So we're going to choose P because that's going to give us the greatest change over the same value of strain. So we're going to say the P, as it will produce a larger increase in lambda r for same increase in strain. So that is fairly obvious just from the graph, but to get the extra mark, you've really got to bring home what that means. Yes, we can see from the graph that a small increase in strain gives a greater increase, but we've got to explain what the advantage that is. So we can say that, so smaller acceleration which produces small changes in strain. Again, what we're doing here is linking the information that we're given in the question about small acceleration to the information on the graph, i.e. small changes in strain. You can't just assume that by saying small acceleration it's going to produce larger changes in lambda. We've got to link that with the information we've been given and say smaller changes in acceleration produce small changes in strain. And so these small changes in strain produce measurable changes lambda r, therefore less uncertainty. Question 15 shows us a ray diagram where we've got some light incident on a glass air boundary. We're told the refractive index of the glass is 1.5, the refractive index of air is 1, and the angle of incidence of the light at the first glass air boundary is 44. It says what is the path of the ray of light. So if we put on some angles, so we know that this one is 44, so therefore this one must be 44, and because we've got a triangle, right hand triangle here, this one must be 46. So the first thing we need to do to work out the path of the light is work out the critical angle. So sine theta critical is n2 over n1. So theta c equals sine minus 1, then it's 1.0 divided by 1.5, so it's our refractive index of the air divided by the refractive index of the glass, and that comes out to be 41.8 degrees. So because 44 is greater than 41.8, or critical angle, then what we're going to end up with is total internal reflection. So the light is going to go this way rather than A, because we've got this angle greater than the critical angle. Now here we've got 46, which is our angle of incidence, and 46 is also greater than 41.8, which is our critical angle. So again, the light is going to go in this direction rather than come out. So because each of the angles is greater than our critical angle, then we're going to get total internal reflectance, and therefore the path that's going to be taken is D. Question 16 shows the rays of light are incident at the same angle theta, and we've got cores of P and Q that have the same refractive index and that the same length, but the core diameters of P and Q, so P is half that of Q. It says the time taken for the ray to travel along the optical fibre P is NL over C sine theta. So we've been asked to say what is the time for the ray to travel across optical fibre Q. Now this is actually much easier than it seems on the surface. Because they're travelling at the same speed, and because this angle is the same in both cases, and the length is the same, but because the angle's the same and the speed's the same, the horizontal component of the speed is also going to be the same. It doesn't matter about the width of these two pipes. The horizontal speed is going to be the same. So because they're the same length, then the time to travel is going to be the same in both instances. So the answer is going to be A. Right. Number 17, the fundamental frequency F is the lowest frequency heard when a stretched spring is vibrating. The spring is now lightly touched 1/3 along its length. What is the lowest frequency heard? So what we've got is we've got a string, and the fundamental frequency is going to look like that, where we have nodes at each end, and we've got an antinode in the middle. Now, if we touch a third along, it's going to look like this. Where this is a third. So now we've got, and it's going to vibrate like that. So now, because we've touched the string at this third along, we can see now that we've got 3 times the frequency, 3 times the frequency, because we're actually reducing the wavelength by a third. So the answer to this one is going to be 3F. Question 18. A diffraction grating is illuminated normally with light of wavelength 6.5 times by 10 to the minus 7. When a screen is 1.5 meters from the grating, the distance between the 0 and the first order maxima on the screen is 0.3 meters. So we've got all that information in the diagram. What is the number of lines per millimeter of the diffraction grating? Okay, so we know that if this is theta here, then theta is going to be tan minus 1, the 0.3, which is our opposite, over the 1.5, which is our adjacent, and that comes out to be 11.3 degrees. We also know that d sine theta equals n lambda. So d is going to be lambda over sine theta for all first order. So that's going to be 6.5 times by 10 to the minus 7 divided by sine 11.3. So that's going to come out to be 3.31 times by 10 to the minus 6. But this is the spacing, so this is D rather than the number of lines per millimeter, and some students took this answer. So to get the number of lines per millimeter, we're going to have to do 1 divided by the 3.31 times by 10 to the minus 6, and that gives us 3.2114. But this is the number of lines per millimeter, and we want a number of lines per this is the number of lines per meter, so we want it the number of lines per millimeter, so we need to divide that by 1,000, which gives us the 3 times by 10 to the 2 to one significant figure. So the answer for this one is going to be C. Here we're told that 2 points on a progressive wave have a phase difference of pi over 6 rads. The speed of the wave is 340 meters per second. What is the frequency of the wave when the minimum distance between the 2 points is 0.12? So if we have a look at a wave, we know that a full wave is 2 pi radians, and we're given that these 2 points here are pi over 6, and we're told that that equals 0.12 meters. So lambda is going to equal 0.12 times by 12, because if this distance here is pi over 6, then because the wavelength is 2 pi, then we're going to have 12 of these gaps for a full wavelength. So that comes out to be 1.44. We also know that F equals V over lambda. We've been told that the speed is 340. We've just calculated lambda. That's 1.44. So that comes out to be 236, or 240 to two significant figures. So our answer is A. Question 20 is going to ask us to look at moments. We're told that a bird sits on a uniform rod suspended from vertical wires P and Q. The weight of the rod is W and is 15 centimeters long. So the weight is going to act down halfway, and that is going to be 7.5 centimeters. We're told that the weight of the bird is 2W, so we've got its weight acting down there and acts at a distance x from P. What is the value of x when the tension in P is half the tension in Q? So if we put on these tensions, so if we say the tension is T in P, then because we know Q is double, we're going to say the tension in Q is 2T. So the weight, total weight down, is going to equal the total tension up. So we've got the weight of the rod plus the weight of the bird equals the tension in P plus the tension in Q. So what we find is W equals T. Okay. So now if we take moments around this point here, we can say that for our clockwise moments, we've got 7.5 W, which is this weight here, plus 2W X, which is this moment here, equals then our anti-clockwise moments are the 15 centimeters times by our 2T. So it'll be 15 times by 2T. So that comes out to be 7.5 W plus 2X W equals 30 W, because we've now just substituted our W equals T. So if we then simplify that, so it's 7.5 plus 2x equals 30. So all we've done here is cancel out the w's all the way through, and we get x to be 11.25 or 11.3 to three significant figures. So the answer is going to be C. So question 1. we're told a car's engine produces a useful output of 6.5 times by 10 to the 4 W. The car of mass 950 kilograms moving uphill at a steady speed. The slope of the hill is 12 degrees to the horizontal and resistive forces are negligible. So if we just put on a couple of angles here, so if we drop a normal to this, then we know that the angle straight down, because of our weight here, so this angle here is also going to be 12 degrees. We also know, because it's traveling at a steady speed, then the force is going to equal the component of the weight that's down the slope. Okay, so this is weight with the component down the slope, and this is going to be our force. So there's no overall resultant force because we don't have any acceleration. So we can work out the force to be 950, which is our mass of the car, times by gravity to give us the weight, which is 9.81, times by sine theta. So this is going to be the component of the weight down the slope, and that comes out to be 1938. Okay, we also know that P equals FV, so V equals P over F. We know that the power is 6.5 times by 10 to the 4, and we know that the force is 1938, so that comes out to be 33.55, or 34 to 2 significant figures. So our answer for this one is going to be C. So the key to this question was realizing that there's no acceleration, so the force and the component of weight down the slope is going to be equal, and then knowing how to calculate that component down the slope, which quite a few students were unable to do. So question 22 says a girl is bouncing on a trampoline. Assume that her resistance is negligible, her acceleration, and we're given various options. So if we think about the girl, her weight is always going to be the same, and it's acting downwards. But the acceleration that she experiences is always due to gravity, and that is always going to be acting downwards. The acceleration due to gravity does not change wherever she is actually on her bounce. So the answer is going to be B, is constant while she's in the air. Now, a lot of students showed limited understanding here of the difference between acceleration and velocity. The acceleration is just going to be due to gravity and always acts in the same direction. So number 23 shows us information about 4 wires and the stiffness of each wire in the maximum strain energy stored in the wire when extended to breaking point. We're told that they're all going to obey Hooke's law, and we're asked which wire extends the least before reaching breaking point. So the value for the stiffness we're given is going to be our K value. Now, the equations that we need for this is E equals half K delta L squared, where delta L is our extension. So delta L equals root 2E over K. So we can see that delta L is going to be proportional to root E over K. So we can calculate this value here given the energy and the K that were given in the question. So if we calculate for each of those, so for example the first one is going to be root 1, which is our energy, divided by 4.0, which is our K, and that comes out to be 0.5. So if we do that for the other ones as well, this one's going to be 0.33, this one is going to be 0.43, and this one is going to be 0.346. So the one with the least delta L before it breaks is going to be this value here, 0.33. So the answer is going to be B. So in 24 we're told that two spheres P and Q have the same volume, but P has a greater mass. The spheres fall in the air and their terminal velocities Vp and Vq respectively, which for us states the relationship between Vp and Vq and the reason. So at terminal velocity, what we have is we've got the ball going down and we've got the weight acting downwards and we've got drag acting upwards. So it's when these two forces are balanced we get terminal velocity. Now drag is obviously to do with air resistance, and the amount of air resistance is related to velocity. So the higher the velocity, then the higher the drag. Now if you've got something that's of a larger weight, then that's going to require a bigger drag before it reaches terminal velocity. So in this case, because we're told that P has a greater mass, it's going to have to reach a greater velocity to get the amount of drag that will equal the weight. And because they're traveling at because they're the same shape, they're going to have the same acceleration, then Q is going to reach equilibrium at a lower terminal velocity because it doesn't have to create as much drag because it has a lower weight. So the answer to this one is going to be D. So question 25 says an aircraft is flying due north through still air at speed V. The aircraft enters a region where the wind is blowing at a speed U from a direction that makes an angle theta to the due south. Okay, so we've got a diagram there. What is the time taken for the aircraft to fly a distance d due north of its current position in this windy region? So if we know that it's travelling v in due north, what we've got to do is find the vertical component of the wind. So because this is theta, then the vertical component is going to be u cos theta. So the resultant velocity north is going to be v minus the vertical component of the wind. So we've got the resultant force equals v minus u cos theta. So that's going to be the resultant velocity due north, because it's got this wind vertical component acting against its velocity. Now we know that time is going to be distance divided by velocity. So if we look at the possible answers, we can see this one has d divided by our resultant speed, which is the v minus u cos theta. So the answer to this one is going to be A. Again, students showed difficulty in resolving vectors, as demonstrated in this question. So 26 gives us a force against time graph for the resultant force on a football, which is initially at rest, and we're asked which of the graphs shows how the momentum of the football varies with time. So what we've got to recall is that force is the rate of change of momentum. So it's proportional to the rate of change, which is delta P over delta T. So the force is going to be, is starting at a low value, it's going to a high value, and then decreasing to a low value again. So what we're looking for is of a graph that's of momentum against time is something that starts with a low gradient, goes to a high gradient, and then back to a low gradient. So if we look at which of these graphs fits the bill, it's only D that starts with a low gradient, goes higher, and then low again. So the answer to this one is going to be D. Question 27 tells us that the objects P and Q are initially at rest at time equals 0. The same resultant force, F, is applied to P and Q for a time T. The mass of P is 10 times greater than that of Q. What is the ratio of the kinetic energy of P over the kinetic energy of Q? So we know that F equals ma. So if the mass of, so we've got the same force, so if the mass is 10 times in P, then that means the acceleration must be a tenth. Okay, because the resultant force is the same, if we increase mass by 10, we've got to decrease acceleration by the same amount. So we'll end up with a lower velocity. Because we're working with kinetic energy, we know that E equals half mv squared. So what we can do is have a look at the ratio of both. So if we've got P, which is 10 times greater for mass, then we have 10 for the mass of P. But velocity is going to be a tenth compared to Q. So we're going to have 0.1. And because this is squared in the equation half equals mv squared, we're going to have that twice. Now for the kinetic energy for Q, the relative mass is just 1 because it's a tenth of P. But the relative velocity is going to be 1 because it's going to be 10 times that of P. And of course that goes in twice. So what we end up with here is 0.1 over 1. So the ratio is going to be 0.1 to 1, which is 0.1. So our answer is going to be A. Question 28 shows graphs of how power is dissipated and how it varies with current in a component that obeys Ohm's law. So because of that, we know that we've got a constant resistance. We also know with P and current, they're related by P equals I squared over R. So because R is going to be constant, we can say that P is proportional to I squared. So what this is telling us is that the larger I is, then the greater P is going to be. So we can discount B and D, but we're also sure that P is proportional to I squared, not directly proportional to I itself. So we can discount this one as well. So the one that's left is A. Question 29 asks us what a kilowatt hour is equivalent to in electron volts. So the first thing we need to do is put that kilowatt hour into joules. So we can say that 1 kilowatt hour is 1000 because it's 1 kilowatt, and it's a kilowatt hour, so we've got to multiply it by 60 by 60 because we want to get it in seconds. So at the moment we've got a kilowatt hour, so to get it in 60 we've got to times by 60 minutes and then 60 seconds, and that will give us 3.600 times by 10 to the 6. And to convert this into electron volts, we need to divide by 1.6 times by 10 to the minus 19, which gives us 2.25 times by 10 to the 25. So the answer for this one is going to be D. Now, a lot of students disregarded the hour in their calculation, so they just converted 1000 into electron volts. Question 30 says the graph shows how the potential difference V varies across an electrical component and how it varies with I. So, and we've been given a tangent. So we've been asked what is the resistance of the electrical component when the current of the component is I2. So we know that R equals V over I. Okay, now if we want to know what V is for a particular current, then we just read that off the graph. So at I2 we can see that the voltage is V2. We don't need the tangent, we just need to read off the graph what the corresponding voltage is at any current. So for this, R is going to equal V2 when I is I2. So the answer to this is going to be C. Right, so 31, a circuit consists of a cell, a thermistor, and a fixed resistor, and 2 ammeters, as shown in the diagram. The cell has a constant EMF and negligible internal resistance. Readings from the 2 ammeters are taken. Which row describes what happens to the current in the ammeter when the temperature of the thermistor decreases? So as temp decreases in a thermistor, then the R increases. So as the R increases, then the current is going to decrease. So we know that the current in this spur here is going to decrease. So we can discount C and D. Okay. Now we're going to have the same potential difference across each spare. So even though the resistance of the thermistor is going to increase, because we've got a fixed resistor across this spur, then we're still going to have the same current flowing through it because the EMF is staying the same. So the current in ammeter 2 is going to remain unchanged. Question 32 says a circuit consists of two identical cells, a resistor, an ammeter and a voltmeter. The cells each have an EMF of 3 volts and the resistor has a resistance of 12 ohms. The cells have negligible internal resistance. Which row shows the readings on the voltmeter and the ammeter? So the potential difference is going to stay the same in any loop. So it's going to be 3 volts, okay, because we've got those batteries in parallel. So we can discount C and D. We also know that current equals V over R. So we know the voltage is going to be 3. We've been told that the resistance is 12. So current is going to be 0.25. So our answer to this one is going to be A. Question 33 is asking which is equivalent to an ohm. So we know that R equals V over I, but we need to get this in terms of where we've got joules and coulombs. So we also know that V equals E over Q. So that's equivalent to having joules from the energy and per coulomb because the charge is underneath here. We also know that I equals Q over T, and that's equivalent to coulomb per second because we've got coulombs on top and time underneath, so it's going to be per second. So if we substitute both of these into our equation for resistance, we have R equals J C to the minus 1, which is our the units of voltage, over C S to the minus 1, which is our units for current. And then what we can then do is, as we bring the coulomb up from below here, that's also going to be a minus 1. As we take seconds to the minus 1 above, that's going to become seconds. So we end up with J C to the minus 2 seconds. So our answer for this is going to be B. So question 34 gives us another diagram showing a circuit with a cell with negligible internal resistance connected in a circuit with 3 resistors, an ammeter and a voltmeter. And it's asking which row shows the readings on the ammeter and the voltmeter. So the first thing we can see is that the voltmeter is connected in series along this branch. Now we know that voltmeters have infinite resistance. So because this has infinite resistance, then we're going to have no current flowing through this branch at all. We also know that I equals V over R. We know that the voltage is 1.5 that's across each of the branch, and our resistance is 20. So we're just taking into account these two resistors in series here because there's no current going to be running through this middle branch. So that's going to be 0.075 amps. So if we look at the options, we know that it's 0.075 amps, so we can discard C and D, and we know that the potential difference is going to be the same across each loop, which is 1.5 volts. So our answer to this one is going to be B.